here's the problem. We've got a function f that is holomorphic, or if you prefer analytic, in a domain omega, and we let g of z be f of z bar or bar. Then the question is g holomorphic and where? So let's answer the second question first. So we'll say that f of z is defined when z is in omega. So that means that f of z bar is defined when z bar is in omega, which is the same as saying that is z is in omega conjugate. So that means, well, if f of z bar is defined, then so is f of z bar all bar. So g is defined in omega conjugate. So that's the where bit taken care of. Now, question is g holomorphic? And the standard way of working out whether g is holomorphic or not is to see whether the Cauchy-Riemann equations are satisfied. So here, let's write, as usual, f of z is equal to u x y plus I times v of xy. That's when z is equal to x plus iy. Now we'll have to do the same for g, but we'd better not use the letters u and v, so let's use the letters r and s. Now, the question is, what is the relation between u, v, and r and s? Well, these are real, these are purely imaginary, so there must be some relation between these two and some relation between these two. Well, the real part of g is the real part of f conjugate of z bar, but that's the same as the real part of f. Real part of f is the same as real part of f conjugate, so that says that rxy is equal to u of x, but is it xy? Well, here there's a z, here there's a z bar, and that says that this is minus y. And in much the same way, we'll get that s of xy is equal to v of x minus y. This is the bit that corresponds to the conjugate, and then there's a minus here because when we get to g, we have to conjugate the f, which means that we have to conjugate ivxy and turn that into minus ivxy. That's where the minus sign is coming from. Okay, so now it's a bit painful to write these xy's over and over again, so I'm going to stop writing them, but always there's going to be this relationship where we've got an r and s with xy, then we've got a u and v at x minus y. But let me see if I can do the Cauchy-Riemann equations. So with respect to x, I'm differentiating this with respect to x, so I'm differentiating that with respect to x, and that's equal to ux. Now I differentiate with respect to y, ry. When I differentiate with respect to y, because of the minus sign there, I get that's minus u of y. Now I do s of x is equal to, there's a minus sign there, so I get minus vx, and s of y is equal to, differentiate, so there's a minus there, but there's also a minus there, and that turns into v of y. So, if the Cauchy-Riemann equations hold, which they do for f, that says that u of x is equal to v of y, and if the Cauchy-Riemann equations hold, it's also true that v of x is equal to, with a minus sign, u of y. And that means that r of x is equal to minus s of y. R of x is equal to plus s of y, and r of y is equal to minus s of x. And that says the Cauchy-Riemann equations hold for g, which makes g differentiable at every point in omega conjugate. In other words, g is holomorphic. That's it.